into Euler equations. So just a quick definition. An equation is said to be an Euler equation if it can be written in the form ax squared y double prime plus bx y prime plus cy equals 0, where a, b, and c are constants. A not equal to 0. So just a quick note here, x equals 0 is a regular singular point of an Euler equation. To solve these equations, we will do something similar to what we did with constant coefficients, second order linear differential equations. Instead of assuming our solution takes the form e to the rx, we are now going to assume our solution takes the form x to the r. So to solve an Euler equation, we will assume that our solution takes the form y equals x to the r, and we will plug in that and its derivatives and solve for r. So if we have y equals x to the r, then we have y prime is just r x to the r minus 1, and y double prime is r times r minus 1 times x to the r minus 2. Then if we plugging into ax squared y double prime plus bx y prime plus cy equals 0, we get a times x squared times r minus 1 times x to the r minus 2 plus b times x r times x to the r minus 1 plus c times x to the r equaling 0. This becomes a r times r minus 1 times x to the r plus b times r times x to the r plus c times x to the r. Factoring out an x to the r, we have a r times r minus 1 plus br plus c. All of this times x to the r equals 0. At x to the r equals 0 only at 0. And then we have essentially the part on the coefficient would have to equal 0. I'm going to give myself a little more space. So to make this 0 everywhere, we wind up getting that AR times R minus 1 plus BR plus C must be equal to 0. This equation here is referred to as the indicial equation. The AR times R minus 1 plus BR plus C is referred to as the indicial polynomial. If we find the roots of this equation, so if the roots are R1 and R2, then we get solutions y1 equals x to the R1 and y2 is x to the R2. Turns out if these are distinct real roots, they do make a fundamental set of solutions. We'll do that more specifically in the next video. But for the moment, let's just assume that we do get a fundamental set of solutions, or we can check the Wronskian for particular cases. So we'll go ahead and find the general solution to the Euler equation, 2x squared y double prime plus 3xy prime minus 3y equals 0. So if we assume that y is equal to x to the r, we wind up getting the indicial equation two is our a times r minus 1 plus 3 times r minus 3 equals 0. This becomes 2r squared minus 2r plus 3r minus 3 equals 0, or 2r squared plus r minus 3 is equal to 0. That we can go ahead and factor if we do a 2r and an r. We do a 2r plus 3 and an r minus 1. This does indeed wind up factoring exactly how we wanted. We would have a plus 3r minus 2r gives us our plus r, and we have our minus 3 on the end. So we can take our r1 to be negative 3/2 and our r2 to be 1. We therefore get that y1 would be x to the negative 3/2 and y2 would be just x to the first power, or x. And then if we want, we can verify this as a fundamental set of solutions. So we have y1 as x to the negative 3/2. Y1 prime would be negative 3/2 x to the negative 5/2. Y2 is just x. Y2 prime is 1. And then if we take the determinant of the matrix y1, y2 as the first row, y1 prime and y2 prime as the second row, we have our Wronskian of y1, y2 is x to the negative 3/2 times 1 minus x times negative 3/2 x to the negative 5/2. This is x to the negative 3/2 plus 3/2 x to the negative 3/2. And we get 5/2 x to the negative 3/2. And this is non-zero as long as x is not equal to 0. at x equals 0, it's just at x equals 0, it would just be undefined, right? So we do have a fundamental set of solutions. On either of the two intervals, -infinity to 0, open, or from 0 to infinity, open interval again. And so we get that y should be equal to c1 x to the -3/2 plus c2 times x. As some of you have mentioned before, it doesn't matter which of those you take as your y1, which you take as your y2. So you could do c1 times x plus c2 times x to the -3/2, and that's also a perfectly acceptable solution. Again, in the next video, we'll go ahead and take a look at the various different solution types we can find.